Hi everyone, today I would like to talk about Gram-Schmidt algorithm. Gram-Schmidt is a very famous algorithm used extensively in digital and wireless communication system to find the orthonormal basis functions, orthonormal basis vectors for your signal. It also has a much more application than communication. It can be used in numerical linear algebra to find whether the set of vectors are linearly independent or not. And if they are independent, to find the orthonormal basis representation of a vector set. Also, it can be used to find the decomposition of any given matrix as a form of QR decomposition, which is going to be discussed in the next video. So in this video, I will talk about Gram-Schmidt algorithm, intuition, and how to actually perform the Gram-Schmidt by hand. So let's start. So as I explained, it can be used, the application of Gram-Schmidt, to find the orthonormal basis vectors. So we usually receive a set of n or k here linearly independent vector, and then after applying Gram-Schmidt, we will find the set of k orthonormal basis vectors, right? So here Q1, Q2, Qk are the orthonormal sets, meaning that by orthonormal sets, I meaning that Qi transpose Qj, if I is not equal to j is 0, if I equal to j is 1. What do I mean by that? Means Q1 transpose Q1 is 1. So each vector has a unit node, right? That's by orthonormal. And Q1 transpose Q2 is 0. Q1 transpose Q3 also is 0, and so on and so forth. But also I said that it can be used to find if the set of k vectors are linearly independent or not. But how? So the way this is done using Gram-Schmidt is that you input set of n vectors, let's say a1, a2, an to Gram-Schmidt algorithm. If the algorithm terminates early, then you claim that these vectors are not independent. So I will talk about what I mean by terminating early. So what the algorithm is very simple. You every time you pick one of these vector, you perform the Gram-Schmidt algorithm. If the algorithm terminates early, then they are not independent. Okay, and therefore they cannot be basis vectors. Okay, so now let's see what is Gram-Schmidt algorithm. So assume I have set of v1, v2, vk vectors that they form some sort of basis vectors, meaning that this v1, v2, vk, they are independent. They are independent, and they span the entire k-dimensional space. Okay. Our goal is to find the orthonormal representation of these basis vectors, or orthonormal basis representation of this set of vectors. Okay. So Gram-Schmidt actually is a very intuitive process. What we do is as follows. At every iteration, we pick one of these vectors. So we start with v1, right? We pick vector v1, and this is vector v1, right? So since there is no other vector in a set, we just have vector v1. We want this v1 to be orthonormal, of course. So we want it to have a unique node. So we go ahead and normalize v1, and we call it u1, right? So u1, anything that can be spanned by v1 can always be spanned by u1, right? Because u1 and v1 have the same direction, right? But different magnitude. So if you can span any thing with v1, you can also span it with u1, okay? But u1 has a unit node. Not correct. So first iteration is easy because there is no other vector in a set. So we don't have to actually care about orthogonality. We just need to check the orthonormality, means that unique node. Okay, now in the second iteration, after I check the v1, I go to v2. Okay, now Now I have in my set, I have U1 and V2. Remember, I replace V1 with U1. Okay, so I want to, U1 is good, but I want to find a vector that is orthogonal to U1 and has a unit norm. So I want to use this vector V2 and find another vector that is orthogonal to U1 and has a unit norm. So let's take a look at this vector V2. This is a vector V2. Or I have it here. I can look at this. This is a vector V2, right? And this is a vector U1. So U1 and V2 cannot be in the same direction. Why? Because remember, this V1, V2, Vk, they are all independent vectors, right? They are bases. So V1 and V2 are independent. U1 is exactly V1, is just they have a different magnitude, but the direction is the same. Therefore, U1 and V2 cannot have the same direction, right? Otherwise, I can just represent V2 as a U1, a constant scalar times U1, okay? And they couldn't be basis vector. Now, so V2 is something like this, and this is U1. Now, I'm looking for this. Let's take a look at this one. I'm looking for this vector. I call this one V2 prime. So V2 prime is orthogonal to U1, and if I can normalize that, then it's going to be a vector that can span the entire plane, and it has a unit norm, and also is orthogonal to U1. So let's see how we can find the V2 prime. So V2 prime is equal to V2 minus the orthogonal projection of the V2 on U1, right? So orthogonal projection of V2 on U1 is this line, this one, right? So it's equal to V2 minus the projection of V2 on V1. Okay, so now we need to see what is the projection of V2 on V1. So projection of A on B in general is equal to A dot B norm of B squared times B. But now remember, this U is a unit vector. We designed it in such a way that has a unit norm. So the denominator is 1. Okay? So projection of V2 on U1 is V2 dot U1 divided by 1, if you want to write that, times U1. Right? So this one. Therefore, this is going to be V2 prime. But V2 prime doesn't have to have a unit norm, right? So it's time to normalize V2 prime. So we just define another vector U2, which is going to be V2 prime divided by norm of V2 prime. And that's the normalized version of the V2 prime. Okay, so this is what I just defined as a note, the projection of A and B. So now I have two vectors in my set, U1 and U2. They each have a unit norm and they're orthogonal on each other. Let me just talk about something here, a notation that I have. So here I set the V2 projection on a subspace V1. So subspace V1 is a space that is spanned by this vector V1, right, by a line. So subspace V1 is just a line, right? So this is a general form that is usually written. It means that V2 projection on the anything that is spanned by this subspace, right? So if you are projecting a vector on a subspace, this means that you are projecting it on every single basis in that subspace. So the only basis for the subspace V1 is U1, right? That's what I just defined it here, right? So you can just go ahead for convenience and change this one to projection of V2 on U1. Okay, very good. So now I have U1 and U2 that are orthonormal sets. Okay, let's take another vector. So let's take V3. Now we take V3, and now I have U1, U2, and V3. Okay, so U1 and U2 are okay, but V3 is a vector that is independent of U1 and U2. Remember, V1, V2, all the way to Vk are bases, and U1 and U2 are derived from V1 and V2. So V3 is independent of U1 and U2, but is not necessarily orthogonal to these two, right? So our goal is to find the representation of V3 that is orthogonal to both U1 and U2 and as a unit node. Okay, so we have two vectors already, U1 and U2. So these two vectors will span a plane, right? So two vectors, so one vector U1 span a line, two vectors U1 and U2 will span a plane. And this is the plane that I have here, denoted by subspace V2. So V3 is not in this plane, otherwise it could be represented by linear combination of U1 and U2. So V3 is somewhere here. So now I am trying to find this V3 prime, this one. You see the V3 prime is orthogonal to the plane, therefore it's orthogonal to every single line in that plane, okay? So what is V3 prime? V3 prime is nothing but V3 minus orthogonal projection of V3 on the subspace V2. Okay, very good. And that's what I wrote here. V3 prime is equal to V3 minus orthogonal projection of V3 on the subspace V2. What is subspace V2? Subspace V2 is equal to a span of U1 and U2. Okay, oh, it's this plane that I draw here. Now, what is that equal to? So if you are projecting a vector on the subspace, it means that you are projecting on every single basis vector on that subspace. Okay, what are the basis vectors of V2, subspace V2? U1 and U2. So we want to project V3 on the basis vector U1 and project V3 on the basis vector U2. So it's gonna be V3 minus, so projection on U1, remember U1 and U2 have a unit node, so you don't have to write the denominator, right? The denominator is 1. So that's a projection on U1, this is a projection on U2. Now, V3 doesn't have to have a unit node. So the last step is to construct U3, which is the normalized version of the V3. So we take V3 prime and divide it by norm of V3 prime, and we get U3. So if you continue this process, then you will find a pattern. Actually, we can also write the pattern already, because after this process, we should visualize a 4-dimensional space, which is not really intuitive. Therefore, we're gonna actually write down the general form of the Gram-Schmidt algorithm. We already can find a pattern here. So based on the first 3 vectors, we're gonna extend it or expand it to the n-dimensional or n vectors actually. So the algorithm is as follows. We receive A1, A2, all the way to AK as a set of vectors. They are our inputs. And our output is the set of K orthonormal vectors, or orthonormal representation of A1, A2, and AK. Okay, so in the first step, we're gonna construct the QI bar. What is this QI bar? Is our representation similar to this V2 prime, V3 prime, right? Why do I call it QI bar? Because I reserve the name QI for the normalized version of that. So you can call this one anything you like. You can call it V2 prime. You can call it V prime, anything you like. So QI bar is the unnormalized version of the vector I'm interested in. Okay, what is it equal to? So QI bar is equal to AI minus the orthogonal projection of AI on every single basis vectors that I derive from the previous iterations. So I'm looking for QI bar. This means I already calculated Q1, Q2, all the way to QI minus 1. I already make sure that they are orthogonal to each other, and I already normalize them, right? So remember this V2 prime. Remember, let's take a look at this V3 prime, right? So V3 prime is equal to V3. This is A3. This is like A. This is like AI, right? minus the projection of V3 on U1 and U2, right? So U1 and U2 are similar to Q1 and Q2, right? So when you define U1 and U2, you make sure that U1 and U2 are orthogonal to each other, and they each one have a unit norm. The same thing is for Q1, Q2, all the way to Qi minus 1. Now we are in the ith iteration, right? So Qi bar is equal to Ai minus orthogonal projection of Ai on every single basis vectors that I have, okay? On Q1 all the way to Qi minus 1. So that's what I have. This is the projection of, AI on Q1. This is projection of AI on Q2, and this is projection of AI on Qi minus 1. Now, remember the denominator is 1. Why? Because the Q1 all the way to Qi minus 1 already they form an orthonormal set. So they have a unit norm. You can write the denominator if you like. It's going to be something like that. Q1 squared, which is 1. So you can write the denominator if you like. Now, if this Qi bar is 0, this means that the AI is independent to A1, A2, and AI minus 1. Or AI can be written as a linear combination of the previous I minus 1 vectors. Remember I said Gram-Schmidt can be used to check whether the set of vectors are linearly independent or not. This is the test that we are going to use. We run the first iteration, this one, of the Gram-Schmidt algorithm. If we get 0, this means that the vector that we are interested, AI, is dependent on the previous vectors. Can be written as a linear combination of the previous vectors. Okay, so this is called early termination. You check, you're done. You realize that the set of vectors are not linearly independent. But what if Qi bar is not 0? Then we are going to go ahead and normalize that. And that's what I reserve the word or the term Qi. Qi is equal to Qi bar divided by the norm of Qi bar. Okay, so it should be norm of Qi bar. So this Qi, for example, is something like Q1. So they are orthonormal. Qi minus 1, we had this, all these vectors, they all have a unit norm. So that was the ith iteration. This is the condition for independence. And this is the normalization condition. Very good. Now let's solve one example together. And let's see how easy is the Gram-Schmidt process. I have 3 vectors in 4-dimensional space. -1, -1, 1. This is V1, -1, 3, -1, 3 is V2, and 1, 3, 5, 7 is V3. So these vectors are independent, right? Or we actually don't know if they are independent or not. We just want to run a Gram-Schmidt algorithm to find the orthonormal sets. First, we want to run a Gram-Schmidt algorithm to see if they are independent, and if they are independent, then find the orthonormal representation of these vectors. Okay, so I pick this vector. You can start from any vector you like. I pick this one. I just go by order. I pick V1 first. I pick V1. The set that I have is only V1. There is nothing else in my set, so I have to only normalize V1. Okay, so I go ahead and divide V1 by the magnitude of V1. How do you calculate the magnitude of V1? Is -1 squared plus 1 squared plus 1 squared plus -1 squared, which is equal to the square root of 4, which is 2. Okay, so V1 divided by 2 is become U1. And this is become -1/2, 1/2, -1/2, 1/2. So this is U1. Okay, check to see whether U1 has a unit norm. U1, norm of U1 is a square root of 1/4 plus 1/4 plus 1/4 plus 1/4, which is going to be 1. So U1 has a unit norm. The next iteration, I'm going to go ahead and pick V2. Okay, now I have V2. I want to find the representation from V2 that is orthogonal to U1 and has a unit norm. So remember, always remember this diagram that we have. This is U1, this is V2, right? This is V2 prime, right? This is V2 prime that I have. So I'm going to write V2 minus orthogonal projection of V2 on U1. So what's going to be equal to? We have this V2, this is V2. Now the dot product of V2 and U1. What's going to be the dot product of V2? It's going to be U2 and U1. It's going to be -1 times -1/2, -1 times -1/2, plus 3 times 1/2, plus -1 times -1/2, plus 3 times 1/2, right? The dot product. And that's what I have here, times U1. If you simplify this expression, you get V2 prime to be equal to this. But remember, V2 prime doesn't have to have a unit norm, and it doesn't have a unit norm. So we let U2 to be the normalized version of the V2 prime. And V2 is nothing but V2 prime, this one, divided by norm of V2 prime, which is nothing but 1 square plus 1 square plus 1 square plus 1 square, which is equal to 2. So we get U2 is equal to 1/2, 1/2, 1/2, and 1/2. Okay, so I have now U2, I have U1. All right, so as a very interesting test, let's calculate the dot product of U2 and U1. So they each have a unit norm, but are they orthogonal to each other? They should be orthogonal. It's going to be 1/2 times -1/2 plus 1/2 times 1/2 plus 1/2 times -1/2 plus 1/2 times 1/2, which is equal to 0. So they are orthogonal. So up to now, our algorithm is correct. Now let's go and pick the last vector, V3. So what is my goal? My goal is to find the representation from the V3 that is orthogonal to both U1 and U2 and has a unit norm. So remember V3 prime, the unnormalized version of the vector that I'm interested in is equal to V3 minus the orthogonal projection of V3 on U1 minus orthogonal projection of V3 on U2, right? So this is V3. This is the dot product of V3 and U1, and this is the dot product of V3 on U2. If you simplify this expression, you get this. -2, -2, 2, 2. Right? This is V3 prime. Again, remember, the V3 prime doesn't have to have a unit norm. So I'm going to go ahead and normalize this. What is the norm of that? What is the norm of V3 prime? It's going to be a square root of -2 square plus -2 square plus 2 square plus 2 square, which is going to be 4. So if you divide the V3 prime by 4, you get again -1/2, -1/2, 1/2, and 1/2. Right? And if you check, you realize that U1, U2, U3 are independent, and they form an orthonormal set. Okay, they are gonna be orthogonal on each other, and they each have a unit norm. Okay, so that's it for the Gram-Schmidt algorithm. In the next video, I'm going to talk about the QR factorization using the Gram-Schmidt algorithm. Thank you so much for listening.